Hey guys, it's Mr. Blake. Today we're going to be talking about mole conversions for yet another day and yet another little twist on it. We've spent the last two lectures discussing first, what the mole is, what the number represents, why we came up with it, why we needed it. And if you don't recall, the reason why we need a unit like the mole is because we need numbers, or we need words that represent numbers that are really, really large. And the reason why we need such a large unit is because the atoms and the molecules that we deal with in chemistry are really, really, really small. So they came up with the mole. And I mentioned it before in class, they did it in sort of a genius way. They already had these different ratios of the atoms. They knew what the atoms weighed, what many of the atoms weighed at the time in the unit that they called AMUs, or atomic mass units. And what they did is they derived through some pretty complicated experiments and some very good math, they derived this number, which they named in honor of Amadeo Avogadro, 6.02 times 10 to the 23rd. And what that number did is it essentially allowed us to use the same number that we were using with AMUs, but now the unit was in grams per mole. So we know how many particles are in a mole. 6.02 times 10 to the 23rd. It's exactly the same thing as saying there's a dozen things, or excuse me, 12 things in one dozen. The word dozen represents 12. The word mole represents 6.02 times 10 to the 23rd. The only time you ever see the mole, and the reason why it's so tricky for a lot of students, is that we only see it in chemistry, because rarely do we need anything that large, or do we need that many of any of those things. So we're dealing with really, really small things, so we can actually have numbers that get up into the, quite a few moles. So it's a useful skill. It will definitely come back. You will see it again throughout the second semester. You will see it again this semester, and you'll really begin to understand the importance as we put it to use. Today's lecture, I just want to talk a little bit before we get into the actual notes, because today's final conversion is a little tricky because it's got some stipulations. Today we're going to be looking at how we convert between mole and volume. And whereas everything else we've done so far, the number of particles in a mole or the number of grams in a mole, really worked for every compound, every molecule, every individual element, today's does not. Volume will only apply to one specific type of molecule or element, and those are gaseous molecules. Now, if you remember from our earlier discussions, gases, what sets them apart from the liquids and the solids, what really differentiates any state of matter, are the distances between the atoms or the molecules or compounds. And gases, by comparison, if we were to zoom in and see gases, and make the atoms visible, blow them up somehow, we would see a lot of gas in the room. Obviously it's enough for a group of people to breathe, to feel wind. By our standards, there would be a lot of gas. But by comparison to a solid or a liquid, gases are really far apart. In fact, if you were to look inside of a balloon, about 99.9% of what is inside that balloon are not gas molecules bumping into each other. They are, in fact, it's just empty space. It is nothing but empty space in there, which is why we're able to move so easily through air. We can pass our hand through air, but not a block of wood or concrete, right? Because those molecules are really set pretty far apart. So I think the thing that's tricky is we assume that things that involve size, like mass or volume, when you have different elements and compounds, like mass, you would assume that when you have a mole of different things, that they would also have a different volume. And that is definitely true for solids and liquids that are packed closely together. Just in the same way, a mole of hydrogen gas has a weight of 2.02 grams per mole. A mole of carbon atoms weighs 6 times as much, and it at 12.01. So that makes sense because, well, hydrogens are lighter than carbon atoms. So if you had a mole of them, of course you would expect those carbon atoms to weigh more. If you had a dozen Mr. Blakes compared to a dozen, Mrs. Blakes, Mrs. Blake is about half the size of Mr. Blake. So if I had a dozen, I would expect a dozen Mrs. Blakes to weigh not as much as a dozen Mr. Blakes. And you would assume that I would also take up more space and volume because I'm bigger. And again, that is true with solids and liquids, but not with gases. Gases, because the distances are so far apart relative to each other, that even though that they're larger atoms, it's the difference in the actual size is negligible. So if you have two atoms, and this is one of our rules here, and this is actually what Avogadro worked on. This is one of his theories. That's why he gets the mole named after him, which is a pretty cool thing. But here's what he comes up with. A mole is approximately, if you're at certain conditions, a mole is going to occupy 22.4 liters. Okay? Now, you think that's a lot. It's actually not that big. We used to have a mole box in the class, and you can actually see it. It's a pretty small little space when you consider, a normal soda bottle is 2 liters. If you had 11 of them and you dumped them out into a box, that's about the space that you would be occupying with Avogadro's number of gas particles. Now, again, the weird thing about this is this only applies to gases. So 1 mole of gas is equal to 22.4 liters of gas, as long as it is at a certain set of conditions we call STP, or standard temperature and pressure. What is STP? Well, it's basically a generic set of conditions that scientists have come up with, and they were able to, under these conditions, calculate, they derived it actually mathematically, how much volume a mole of gas would occupy. So they used a gas law that we'll learn later on in the year to come up with this number. But here's what it is. STP represents standard temperature and pressure. And it is 0 degrees Celsius, or 1 atmosphere. When we get to the gas laws, we're not going to refer to things in Celsius. We'll use the unit of Kelvin, because that's going to allow us to get away from negative numbers, which can throw off our equations. But for now, just think it's 0 Celsius, so the freezing point of water, and 1 atmosphere of pressure. If you don't know what atmospheric pressure is, it's basically our pressure here in California. It's sea level and without any storms. So we're pretty close in Fullerton. We're right around sea level. We're, I think, a little bit above it, but not much. So a normal day in Fullerton is about atmospheric pressure, as long as we're not having some weird weather. So this is a conversion factor, and you can see the question here: how many moles of helium gas will occupy a volume of 149.3 liters at STP? So what we really want to pay attention to, guys, is this idea here of being at STP. Okay, what does that mean? Okay, STP, standard temperature and pressure, because honestly, the only time that you're going to see this conversion factor of 22.4 liters per mole of gas, any mole of gas, doesn't matter if it's carbon, doesn't matter if it's hydrogen, doesn't matter what it is. Anytime that you're going to see that, or I should say the only time you'll see that, is when those conditions are at STP, or standard temperature and pressure, 0 degrees Celsius, 1 atmosphere of pressure. All right. But now that we have seen that, okay, we can again focus in on just treating this like every other conversion factor. Okay? So it's no different than molar mass. It's no different than the number of particles. I'm going to start with a certain known number here, 149.3 liters. That's what I know. What I'm being asked to find is moles, right? Being asked to find moles. So here we go. We're going to start with what we know, and then we're going to simply work down, okay, until we get what we want. So my known 149.3 liters of helium, and I want to reiterate this, guys. This says helium. It could literally be any other gas. Okay? If you're looking at the periodic table and it's just an element, the gas would be in red. We're not going to trip you up or give you any really tricky questions. We will tell you it's a gas. We wouldn't mention STP if it wasn't. The unknown is how many moles that is. So this looks a lot like the things that we've been doing so far, right? We're giving you some unit and asking you to convert into moles. Or we're giving you the number of moles and asking you to convert into a specific unit. either way, you're always going to set it up the same way. We start with the number given to us. So we bring that up. That's 149.3 liters. Some people like to put the 1 down there just to make sure that they're keeping things straight. It doesn't really matter to me, to be perfectly honest. Then, how many liters are in a mole? So my conversion factor. Now, only for gases and only gases at STP. But there are 22.4 liters in a mole of gas. My liters cancel. Notice I put liters on the bottom because I wanted that unit to cancel. I will be left with moles of helium gas. So now, if I look back to what I had in the question here, I had 149.3. That is 1, 2, 3, 4 sig figs. So when I go to my final answer also has 1, 2, 3, 4 sig figs. Also note, guys, that when I do this, I don't just write moles. I write moles of whatever my substance is. Okay, so that actually matters. On your test, you have to do this. All right. Let's look at another example here. So let me click out of here. Okay. So we've already seen how to convert moles into particles. We saw how to convert moles into mass using it as a conversion factor, right? 1 mole is 6.02 times 10 to the 23rd atoms, molecules, formula units, which again is just a fancy name for an ionic compound. We can't really call them molecules because they don't use covalent bonds. We also learned how to calculate the molar mass using those numbers on the periodic table. We call those numbers, if you're looking at the mass of an atom, it's AMUs, but if you're looking at the molar mass, it is the mass of 1 mole, we're going to be in atomic mass in grams. So that's how many grams per mole. Now, our third and final, lucky you, conversion factor is going to be 22.4 liters in a mole. Now, the other two work for everything, but you really, guys, it's important that you remember this only works for moles of a gas. Okay, not only a gas, but a gas at standard temperature and pressure. So the question really, it's important that when you read the question that it specify that the conditions are at STP. If they were not at STP, you could not use 22.4 liters per mole. We wouldn't know. You would have to use something called the ideal gas law, which you'll get to learn, but we don't know it just yet. So those are the three, and what we'd like to do now is sort of link them all together, right? What you guys have in front of you in your notes is what we call a roadmap, okay? And the thing, we've been kind of preaching at you, and it's hard to see it, hard to see the forest through the trees sometimes, is how important the mole as a unit of conversion is, okay? How it allows us to relate. And in the next unit, when we start talking chemical equations and stoichiometry and reaction rates and ratios, the mole is even more important. You're going to see it. You're going to really see it literally for the end of the year. So when you're looking here at the mole, sorry, some of the some of those, the S's are dropped to the bottom, but all of them convert to the mole. So if I want to convert volume of a gas to a mole, it's 22.4 liters is equal to 1 mole. That's my conversion factor, all right? And I can set that conversion factor up with whichever part of that I want in the numerator or the denominator, whatever's going to make it work. I can convert particles. Now, again, you could literally do any particle, but as we've kind of talked about, the only particles you really realistically ever have a mole of, or the need to use the unit mole, would be something as small as atoms or molecules or formula units. So you're not going to see it with, you're not going to go to the grocery store and buy a mole of, anything, because you cover our country miles and miles deep into outer space with whatever you chose. So even grains of rice, you'd be burying the planet. So that would be bad. The last one, and the one honestly that really gets used probably the most, is molar mass in grams. And so that's an important one. It's how many moles, how many grams a mole of something weighs. So sometimes it's nice and easy and they give you just the element, and then other times they're going to give you a compound, and you'll have to add all of the different molar masses from the periodic table up. But these are the three conversion factors, and you can see they all pass through the mole. So if I were given something in, let's say, particles, right? Let's say they told me how many atoms I had, and let's say it was actually of a gas, right? So they started me over here in particles, and they wanted me to say how many liters, or I mean, it could be really any unit of volume. To be honest, it could be milliliters. They could change it on you. We could get more and more complex. But let's just keep it easy, and let's say they wanted to know how many liters of gas, would you have if they gave you X number of molecules of, pick your favorite gas, and or atoms of neon. Well, I would simply then go from particles over to moles, okay? And once I convert to moles, I can then go from moles to volume, okay? And that's how it works. If I wanted to go from, let's clear this, and let's say you wanted to go from mass. Let's say they told you how much it weighed, right? They told you, hey, I got a gas and it weighs 37 pounds. Well, okay, how many liters of gas is that if it's at STP? Well, you would go from mass, obviously you'd have to convert pounds to grams, right? You'd have to do some other dimensional analysis first, but then once you were in grams, you can use this conversion factor right here in grams per mole. That would get me into moles, and then from moles, again, I could actually tell you pretty close. It wouldn't be exactly 100% accurate, but I could get pretty close and tell you how many molecules or how many liters of gas you would have. So it's really, really flexible. Primarily, we're going to stick with the units that you see: liters, atoms, and grams. But if I wanted to be mean and a little trickier, I could, of course, then make you convert into different units of volume or different units of mass. It wouldn't be really that outrageous, and you'll probably get one or two of those. So let's give it a look. Last problem here. What volume would 4.32 times 10 to the 23rd atoms of krypton gas occupy at STP? All right. So again, the key here that we're looking for, guys, the key that I want you to notice right out the gate, right? STP. So STP tells me I need to be thinking it's a gas, right? And that I can use the conversion factor, 22.4 liters per mole. Okay, that's a helpful thing. All right, that is your conversion factor, right? It's probably going to be used. They wouldn't have mentioned STP otherwise. Now, sometimes, to be honest, sometimes they'll throw in that information to sort of mislead you. So it is really important that you kind of get your head straight and think it through. But let's look here. We're going from volume, right? So before we even bring this up, let's just write it down here. We're going from atoms, right? We're going from atoms to what? Okay, what are we going to convert to? Well, if you go back and look up at that little bit you just filled in, what we call the roadmap, what does everything pass through? And this is the habit we want you to be in really for the rest of the year. Everything goes through moles. Everything goes through moles. So convert from atoms to moles. Now, once you're in moles, you can go anywhere. And what do they want us to do? They want us to go into volume. Well, what are the conversion factors that are going to get you there? All right, let's look. So let's settle in here, and we'll see where this is going to take us. Okay. Our known, 4.32 times 10 to the 23rd atoms. So my unknown is liters. Now, if you look at that roadmap, you're not going to see anything that takes us directly from atoms to liters. It doesn't exist. All right? There's no relationship there. The thing that relates all of these things are moles. Moles are, it's like that friend who's friends with everyone. If you're trying to get a hold of someone who you may not be friends with, but you know someone who is, there's always that guy or that girl in your life. That's the mole. Kind of like friends in lots of different areas of lots of different walks of life. That's the mole. The mole is a mover and a shaker. So we always want to convert to moles. All right, so the atoms, how many atoms are in a mole? So this takes us back to last week's lectures. There are 6.02 times 10 to the 23rd of anything, including atoms, in a mole. Because I want atoms to cancel out, I'm going to put that portion of the conversion factor on the bottom. So atoms have canceled. If I stop the calculation and just worked it now, I'm going to be in moles. Right? Well, now, okay, I want to go from moles to, and again, keep in mind, go back to that unknown. What am I really looking for? I'm looking for liters, and it's at STP. Well, do you know how many liters of gas are in a mole when they're at STP? You do. There are 22.4 liters of krypton in 1 mole of krypton. Sorry, another little typo there. Krypton should obviously be up. So moles of krypton cancel. And now what I'm going to do, and if you're following along in your calculator, you're going to punch it in this way. 4.32 times 10 to the 23rd times 22.4 divided by 6.02 times 10 to the 23rd. Okay? And in that sequence, if you follow it and then you look back at the question, go back to your known, how many sig figs do you have there? 4.32 times 10 to the 23rd, you're going to have 3 sig figs. So 16.1 liters of krypton. Okay? And that's going to be your final answer. And again, I want you to notice, not only did I write down the unit, but I wrote units of, and I named the species. I named the substance that I had that volume of. I said krypton. I didn't just drop it at 16.1 liters. Really important. It's going to count for points on your test, which is written. All right, guys. So the next thing we're going to get into is balancing equations, but I'm going to save that for a little bit later. You may or may not get this as a screencast. I know I went on a little bit long, but I wanted to initially go through and just kind of make sure you understood the whole idea of why volume is so unique and why it's not, why we need to be careful with it. We can't just convert anything. It's got to be a gas, and it's got to be an STP to use that conversion factor. Otherwise, no go. All right. Thanks.